Hi everyone, welcome to my YouTube channel again, and in this video I'm going to make a quick summary of doping of semiconductor materials and a PN diode. So let's begin with the doping of semiconductor. To know about the doping of semiconductor, we have to know some chemistry. So let's see, we call this vertical part group 3, and here in the middle group 4, and in the last we call it group 5. So what means group 3, group 4 or 5? Group 3 means if there is an atom, let's see for the boron or aluminum. Let's look at the aluminum. It has 13 electrons, which means in the outermost space they have only 3 electrons left. Also for the gallium and indium or boron, all these 4 atoms have 3 electrons left in the outermost space. So we recall it group 3, 4, 5 depending on how many electrons are left in the outermost space of the atom. Now, to understand the doping of semiconductor materials, let's have a look with the group 5 material, phosphorus. So if there is phosphorus in the middle, and if it wants to get a covalent bond with the silicon, of course silicon is located in group 4, which means it can get bonded. If there is 1, 2, 3, 4, 5 silicon, they get a covalent bond, as you can see, because they have 4 electrons in the outermost space. Whenever that they get bonded with another silicon, it is very stable. However, with the phosphorus, because phosphorus is located in group 5, they get bonded with silicon, and because they have 4 electrons left, 1 electron will be left some in any place, and we call this free electron. Now let's have a look with the group 3 materials getting bonded with the silicon. Let's have a look with the boron. Because it is group 3 material, they have 3 electrons in the outermost space. However, because silicon have 4 electrons, when they get bonded together, 1, 2, 3, 4, 1 electron is missing. Therefore, materials like boron located in group 3, they need to get electrons into their space. So we call this group 3 material the acceptor. And for the group 5 material, because they have 1 more electron in the outermost space, we call it a donor material. To extend to our semiconductor knowledge, we call the group 5 material N-type material, because they have 1 more negative charge. We call it N-type because N stands for negative. And for the P-type, we use it as with the group 3 material, as you saw it in the previous what I mentioned before. So we call these group 3 materials acceptor, and P-type is associated in this part. Why we call it P-type is because materials like boron, which is located in group 3, they are missing 1 electron, and because they are negatively ionized and they have more whole pairs, so it stands for positive, so we call it P-type. And as you can see, there is a valence band and conduction band and Fermi energy level shown here with two diagrams. Before I start explaining about it, you need to know about what is Fermi level. So Fermi level stands for is the position where the electron can exist in the percent of 50%. So this point will be the 50% part where the electron can stay. So this is the diagram for at the 0 Kelvin without any optical or thermal energy. Fermi level will be located in just the middle of the conduction band and valence band, because the definition of Fermi level was where electron can exist in the 50% position. And by the way, if we can know that Fermi level also depends on the temperature. So if the room temperature gets higher, it will be very little, but Fermi level will also increase a very tiny little bit. So let's get back to the group 5, group 3, or we call it donor acceptor, or we also called it the N-type and P-type. So let's look at it. For the N-type, because there are a lot of electron, because it is group 5, the Fermi level are located close to the conduction band, because it is because the electrons are higher than the 50%. So the Fermi level got increased. But for the group 3 materials, they only have 3 electrons in the outermost space. It means that it has less electron than the 50%, so the Fermi level gets very close to the valence band. So this basic knowledge is quite you need to know, and you must remember it. Now we saw each of the energy level, and now I'm going to introduce you with the PN diode. It's not that hard if you follow it step by step. The most important thing is you need to know how to draw the PN diode diagram. So as I told you, this diagram is for the N-type, because the Fermi level is higher than the 50%, and this is for the P-type. So now how do we draw this diagram? First, the most important thing is we need to assume that it is in thermal equilibrium state. So this means if it is thermal equilibrium, I told you that the Fermi level needs to be constant in the previous slide here. So let's have a look. Yeah, so the Fermi level is constant. This is the most important thing. And how you draw is you just draw one by one. So here it is the Fermi level, and because for the N-type, the Fermi level was very close to the conduction band, so we draw conduction band near to the Fermi level, and the lowest one will be the valence band. And for the P-type, we draw Fermi level. Because it is constant, you have to move the valence band near to the Fermi level and just draw the conduction band. It's easy, and then you just have to connect them. Yeah, now we have to look with the charge and the electric field and electric potential energy, because by the Poisson equation, if you integrate charge, you get the electric field, and if you integrate electric field, you'll get the potential energy. So this is the quick diagram for it, because in the middle of this line, this indicates for the n-type, because n-type n-type gives electron, they will be positively ionized, and this is the charge. I drew it. And here, because p-type gives electron and they get negatively ionized, so it is drawn under 0. So this is the charge, and if you integrate them, you'll get this kind of curve, and this means the electric field. And as you know, in this point at the peak, you'll get at the junction boundary, you'll get the electric field maximum value. And if you integrate them, you'll get this kind of curve of potential energy. I'll give you some definition of this diagram. The part in the n-type, we call this part a neutral region. Because we call it neutral region is the mobile carrier and the electron that was stayed here will get deleted, and they will stay neutral. And between the n-type and p-type, in the junction point, we call it the depletion region. Near the depletion region and neutral region, you'll get your own mobile carrier located next by, and because of the electric field, because of the attractive force, the electric field will flow this arrow point. Yeah, so this is it for this diagram. And now let's have a look when you bias the PN diode. So this is the diagram for in a thermostat, and this diagram is for the when you give a bias with the reverse bias, and this diagram is for the forward bias, and this diagram is for reverse bias, forward bias, and when it gets tunneling. So let's have a look step by step. Okay, so you may question to me, what is this kind of drawing? It means the Boltzmann tail, and it indicates the amount of electron or the amount of hole. So if it is bigger, it means it has a lot of electron in this space, and also here it means it has a lot of hole in this space. So what it means by giving a reverse bias means we call this point the built-in voltage. So what it means to give a bias is when you give a bias to the built-in voltage, it gets a junction potential. So reverse bias means you give a positive charge to the n-type part and the negative charge to the p-type part. So this diagram is for the reverse bias, and if you give a reverse bias, as you can see, the junction point gets much more increased than before in the thermal equilibrium status. If you give a minus charge, I mean the negative charge, the mobile carriers will be located near here negatively, and here positively. And there will be a lot of built-in charges, because if you give a reverse bias, the depletion region will increase, and because of it, the electric field will be higher because the potential energy is high. So how we can relate with potential energy and electric fields, I mentioned in the previous slide. If you derivate the potential energy, you get electric field. So you can see the slope got increased a lot, so the electric field will be higher. Now let's have a look with the diagram when you give a forward bias. As you can see, the junction potential got lower, which means a lot of electrons can pass by to p-type conduction band. It gets increased exponentially, and as you can see, for the forward bias, you get electron in the exponential function.